signal. The general representation of set of M carrier phase modulated signal is this one. So the only difference is over here. We are introducing a 2 pi M over M. Okay. So this is the general expression for phase modulation. GT is the baseband pulse shape which determines the spectral characteristics of the transmitted signal, as will be demonstrated in chapter 8. When G of t is a rectangular pulse, then it can be represented by this one. The amplitude of this pulse is this expression. So we put this expression over here and get the corresponding transmitted signal waveform. So we have phase modulation. And you can see that this phase modulation has constant envelope. This amplitude is not changing. The only thing that is modulated is phase of the carrier. Phase of the carrier. So this is the final transmitted signal. This type of digital phase modulation is called phase shift keying. So the new term is now PSK. Figure 7 point illustrate a 4-phase M is equal to 4 PSK signal waveform usually called a quadrant PSK or QPSK signal. Figure 7.18 is this one. So we have 4 phase input changes. So the signal is coming, then we have 180-degree phase shift, then another phase shift, then another phase shift, and then another phase shift. So this is the example of 4 PSK. If we expand this signal, so by viewing the angle of the cosine function in equation 7.314 as the sum of two angles, so we can expand this thing cosine alpha plus beta, okay. So we can express this UM or the band pass transmitted phase modulated signal like this one. You can easily get this. So now he has changed this AMC and AMS. AMC and AMS are given by this thing. So if you apply cosine alpha plus beta on this expression, you will get expression of phase modulation, QPSK. So this is very important equation. In this case, GTs are same, cosine 2 pi FCTs are same, but the only thing different is AMC and minus AMS. So these are coming from this expression. So what is AMC? AMC is cosine 2 pi M over M, and AMS is sine 2 pi M over M. So again you see that this is a two-dimensional, cosine 2 pi FCT and minus sine 2 pi FCT. So this is a two-dimensional representation again. So digital phase modulation is a two-dimensional two-dimensional constellation diagram. So you can also look at this as two amplitude modulated quadrature carriers. So this is a carrier, this is another carrier of same frequency FC. Only difference is this is cosine, this is minus sine. So they are quadrature carrier. So one is along this. So AMC GT is transmitted with this carrier. AMS GT is transmitted with this carrier. Okay. So in this case, now we have previously the signal constellation points were just ES, but now we are adding this cosine 2 by M over M and ES under root sine 2 by M over M. So this is the geometric representation of two-dimensional vectors with components this. Okay, so this is along the x-axis, this is along the y-axis. Note that the orthogonal basis functions are, one is cosine based function, the other is sine based function. So orthogonal basis functions are just sine and cosine. Signal point concentration for m is equal to 2, 4, 8 are illustrated in figure 7.20. So if we take m equal to 2, we get this thing. So they are 180 degree out of phase. If we took this one, m is equal to 4, this is 4 psk. They are separated by each other by an angle of 90 degree. Okay, 4 psk. So the angle from this vector to this vector is 90 degree, and from this vector to this vector again it is 90 degree. So this is the 4 psk, and they are all equal length vectors with this expression. See, so the only thing, the amplitude remains same. Amplitude of this vector is same as this one. Similarly, this vector and this vector remain same, but their phases are changing. So in this case, 180 degree phase, 90 degree phase, and in this case, what is the phase of this is 8 psk. So you are, so this is so if you look at this, 360 divided by 4, so 90 degree. And if you divide 360 by 8 points, so you will get the corresponding phase. So in this case, we are transmitting just one bit, 1, 0. In this case, we are transmitting two bits, 0, 0, 1, 1, 1, 1, 0. So if you move from 0, 0 to 0, 1, so you are just changing one bit. So this first bit is changed over here. If we move from 0, 1 to 1, 1, then this second bit is changed. If you move from 1, 1 to 1, 0, this second bit is changed. So this is called gray coding, this gray encoding scheme, where you just change a single bit. Adjacent phases differ by one binary digit. So the scheme, how the bits are represented, they are represented using gray encoding scheme. So this is 2 psk, 4 psk, and this is now the diagram for 8 psk. So the other important thing is to find the Euclidean distance between any two signal points in the constellation. So you just take 2 points and then take their difference. Okay. So and then take the under root, square them, and then take the under root. So you will find the minimum distance. So the minimum Euclidean distance, or the distance between two adjacent signal points, is simply this expression. So it is changing by this cosine of 2 pi over n. So minimum Euclidean distance plays an important role in determining the error rate performance of the receiver that demodulates and detect the information in the presence of additive wide Gaussian noise. So for all modulation schemes, we should be able to find the minimum Euclidean distance between any two signal points, because this greatly affects the error performance, or the probability of error or bit error rate of the receiver. Receiver has demodulation and detection blocks, and we are talking about the presence of additive wide Gaussian noise. So this will be our next topic. These things will be covered by Dr. Mohammad Adnan. And first, I will go through the receiver structures. After covering these topics, we'll go towards the receiver structures. And once we know what is an optimum receiver in AWDM channel, then we go for its performance. So at that point of time, these Euclidean distances will be very important. So we have covered now one-dimensional and two-dimensional modulation schemes, mainly PAM and PSK, phase modulation schemes. So PAM and then the PSK and its variants. Now we move towards another two-dimensional band pass signal, which is called QAM, quadrature amplitude modulation. So in this case, quadrature amplitude modulation, now you got sufficient idea that from baseband to band pass signal, how we construct this UM. So in this case, now we are using the same scheme AMC cosine 2 pi FCT, AMS GT sine 2 pi FCT. This is the transmitted signal in case of quadrature amplitude modulation. We are using two quadrature carriers. One is cosine 2 pi FCT and the other is sine 2 pi FCT. So this type of digital modulation is called QAM. So in case of carrier phase modulation, we observed that the band pass signal waveform may be represented by those equations in which the signal waveforms are viewed by two orthogonal carrier signals. However, the carrier phase modulation signal waveforms are constrained to have equal energy, which simplifies that the signal points in the geometric representation of the signal waveform lie on a circle of radius this way. If we remove the constant energy restriction, we can construct signal waveforms that are not constrained to fall on a circle. So you see that what is the difference between PSK? So they are all over a circle of unit of this radius. See? So this is 8 PSK, this is 4 PSK. If we remove this restriction, then basically what we are talking that we are changing the amplitude as well as the phase. So AMC and AMS are the set of amplitude level that are obtained by mapping k bit sequence into signal amplitude. For example, if we look at figure 7.21, this represents 16 QAM. 16 QAM is over here. So in this case, it is not a circle, but it is a square. So amplitudes are changing as well as the phase. So this is the example of 16 QAM. In general, the rectangular signal constellation results when two quadrature carriers are each modulated by a PAM signal. So two quadrature carriers, sine and cosine, they are modulated by PAM signal. This is PAM because this is the amplitude is changing. So two quadrature carriers are amplitude modulated by the PAM signal. So more generally, QAM may be viewed as a form of combined digital amplitude modulation as well as digital phase modulation. In this case, in case of PSK, we have only phase modulation, no change in amplitude. Now QAM is actually a combination of PAM and PSK because in this case we have combined digital amplitude as well as phase modulation. So this line is the key thing. It's very important that you understand the difference between PSK, PAM and QAM. Thus the transmitted QAM signal waveform may be expressed as this way. So in this case we have UMN. So amplitude is modulated by this factor AM and phase by theta n. So AM, M varies from 1 to M1 and N varies from 1 to